Example. The idea is this: if you happen to have two metal ions, copper, lead, are the KSPs so different that you can actually use an anion that you know will precipitate both, but will precipitate one before it precipitates the other? That's the idea. It's one of the things that we do in basic analytical chemistry is you have a mixture of ions, you need a way to separate them out. Well, you can separate them out because of different KSP values. Certain things will fall out as a solid, will precipitate before others do. So let's just do a problem. Example: a solution contains 1.1, oops, man, I'm getting sloppy with my writing, aren't I? Jeez. 1.1 times 10 to the negative 4 molar copper 1 ion and 2.1 times 10 to the negative 3 molar lead 2 ion. If iodide is slowly added to this solution, will PbI2 or CuI precipitate first? Okay, and also at what concentrations of iodide will each salt start to precipitate? Will each salt start to precipitate? Okay, so let's see what's going on pictorially real quickly. We have this solution, and we have some lead ion in there. We have some copper 1 ion in there, 2 plus, copper 1 ion. We're going to be adding iodide ion. Well, we know that copper iodide is insoluble. We know that lead iodide is insoluble. Well, they have different KSPs, so ideally, I should be able to precipitate one before the other based on the difference in KSP. Because again, once the concentration of iodide, and let's say for copper, is such that it equals the KSP, it's at that point that a precipitate starts to form. Because a precipitate means it's in equilibrium now with its solid. It's reached its saturation point. There's no more of the iodide and copper that can be in solution together. The rest of it is just going to fall out as solid copper iodide. And the same for lead. Okay, so let's go ahead and write the KSPs for these. KSP of PbI2, just as a reference, is 1.4 times 10 to the negative 8. And the KSP of CuI is equal to 5.3 times 10 to the negative 13. Now you might think to yourself, well, wait a minute, why can't we just compare? We know that, one of them is going to precipitate first, probably this one, simply because it has a higher KSP. Well, the problem is PbI2 and CuI, you can't compare them directly. And the reason is because they don't produce the same number of ions upon dissociation. So you have to run the mathematics. If they actually produce the same number of ions, then yes, you can use the KSP when we discussed relative solubilities. You remember 2 lessons back. But here you have to run the mathematics. Okay. So let's do PbI2. PbI2 is going to be in equilibrium with Pb2 plus 2I minus. The KSP expression equals Pb2 plus times I minus squared. Well, we know the KSP is 1.4 times 10 to the negative 8. And we know the lead concentration. It says that the lead concentration is 2.1 times 10 to the negative 3, right? It gave us the concentration in the problem. So 2.1 times 10 to the negative 3. So it's a simple question of algebra to find out the iodide ion concentration. And in this case, the iodide concentration is 2.6 times 10 to the negative 3 molar. That means when the iodide concentration hits 2.6 times 10 to the negative 3 molar, that means based on the amount of lead that was already in there, it'll match the KSP, and at that point, that's when the precipitate will start to fall out. Not until then. So if I have 2.6 times 10 to the negative 4, 10 to the negative 5, anything less than this, there will be no precipitate. That's the idea behind the KSP. The KSP tells you when the precipitate will form, when it's in equilibrium with the solid. Okay, now let's go ahead and do the copper iodide. Copper iodide is going to be in equilibrium with copper plus iodide. Be very, very careful. You have copper plus and copper 2 plus. Make sure you don't mix them up. They're actually different ions, different compounds, different solubilities. Okay, so the KSP for this is equal to 5.3. Well, I'm going to use that number in a minute. Let me just write it out, the expression. Plus times I minus, each to the first power. So we have 5.3 times 10 to the negative 13 equals, well, they gave us the copper ion concentration to begin with. You know, what's floating around in solution was 1.1 times 10 to the negative 4. And then just multiply by the iodide concentration. The final iodide concentration equals 4.8 times 10 to the negative 9 molarity. Okay, here we go. Here are the two numbers that we need to compare now. As we add iodide to this solution that has lead floating around and copper floating around, these calculations based on KSP and the KSP expression tell me that when the concentration of iodide that I have added equals 4.8 times 10 to the negative 9 molarity, copper iodide will start to form, will start to precipitate as a solid. If I keep adding iodide, when the iodide concentration reaches 2.6 times 10 to the negative 3 molarity, at that point, the lead iodide will start to precipitate. So, in this particular case, CuI, copper iodide, will precipitate first. This gives us a fantastic analytical method for actually taking a solution with a whole bunch of different cations in it and using different reagents, like in this case iodide, to actually separate out these ions, because that's what we do in chemistry. Most chemistry is just a mixture of things. A huge part of chemistry and biology involves the notion of separation. I need to purify things. I need to separate them into their individual components. In nature, things don't come just individually. They come in one big mess that's all mixed up. Half of chemical science is based on the notion of separation. So there you go. Iodide, if there's a solution that's a mixture of lead and copper, iodide is a fantastic reagent in the form of sodium iodide, potassium iodide, any iodide source will do, for separating out these two ions if I happen to want to separate out these two ions. This is what we mean by selective precipitation. I'm going to precipitate this before I precipitate that. That's the idea. Okay,